Inside the world's first flying car factory in China, you're standing in a facility that's producing over 10,000 passenger aircraft every year. You heard that right, 10,000 flying cars. To put that in perspective, that's more eVTOL aircraft than all of the world's aerospace manufacturers have ever produced combined. Right now, while Western competitors are still waiting for government approval to fly, China's factories are rolling units off assembly lines, loading them onto trucks, and preparing them for commercial operations. And this isn't a glimpse into the distant future. This is happening today. Let's walk inside XPeng AeroHT's Guangzhou facility and see exactly how they're making it possible. XPeng AeroHT's Production Revolution. You step onto the factory floor of XPeng AeroHT's Guangzhou facility, and immediately, something strikes you. This doesn't look like a laboratory or a research center where engineers tinker with prototypes in clean rooms. This is a real factory. Modern assembly lines stretch across 190,000 square feet, divided into 4 specialized workshops: the composite shop, the joint shop, the painting shop, and the assembly shop. And right now, you're watching the world's first mass production facility for flying cars operate at full scale. The modular flying car, called the Land Aircraft Carrier, is a 2-part system, and what you're seeing being assembled here is the critical component, the detachable electric aircraft. Each unit represents months of engineering compressed into a manufacturing process so refined that the factory can produce 1 complete aircraft every 30 minutes. You heard that right. Every half hour, another flying car rolls off this line, fully assembled, fully tested, ready for integration with its ground-based mothership. Watch the engineers move through the composite shop, where carbon fiber structures are layered and molded. This isn't aluminum or steel. Carbon fiber is essential because every pound matters when you're trying to achieve vertical takeoff. The material science here is aerospace grade, but the manufacturing philosophy is pure automotive. They're applying the same lean production principles that made Chinese EV factories the fastest in the world, and they're applying them to aircraft. The tension is building because while you're watching this happen, companies in the United States and Europe are still assembling prototypes in converted hangars. They're testing, they're iterating. They're chasing government certifications that could take another 5 to 7 years. Meanwhile, XPeng AeroHT isn't waiting. They've already received nearly 5,000 pre-orders for the Land Aircraft Carrier. They're targeting mass deliveries in 2026. But here's what makes this truly revolutionary: the distributed electric propulsion system. Instead of 1 or 2 massive rotors, the aircraft uses multiple smaller electric motors arranged for maximum redundancy and efficiency. If one motor fails, the others compensate automatically. If one battery cell degrades, the system redistributes power. This is engineering paranoia designed into the hardware, the kind of safety-first thinking that turns a flying car from a stunt into something your grandmother might actually ride in. The factory floor hums with purpose. Precision measurement systems track every component from supply chain to final assembly. Solar panels cover the roof, powering the facility with renewable energy. This isn't just production. This is a statement. China is building the infrastructure for a transportation revolution, and it's happening not in some distant future, but right now, in this factory, on this assembly line. With each aircraft rolling off every 30 minutes, the autonomous blueprint, EHang's EH216. You leave XPeng's facility and drive to EHang's Yunfu production center, where you encounter something fundamentally different. While XPeng builds modular flying cars with optional pilot control, EHang has chosen a radically different path: complete autonomy, no pilot, no joystick, no human intervention whatsoever. You're looking at the world's first commercial autonomous aerial vehicle actually in production, and the engineering required to make this work is staggering. The EH216-S sits on the assembly line like nothing you've ever seen. A sleek multi-rotor aircraft designed to carry 2 passengers who do nothing but sit down and enjoy the ride. The autonomy systems are doing everything: flight planning, obstacle avoidance, real-time weather assessment, emergency protocols. Over 76,000 autonomous flight hours have been logged. You heard that right. This aircraft has proven itself through sheer volume of testing that most manned helicopters will never achieve in their entire operational lifetime. Inside the factory, precision becomes obsession. Every sensor must be calibrated to within millimeters. The flight control computers undergo redundant testing. The battery management systems are monitored with medical device-level scrutiny because a single software glitch doesn't mean a rough landing, it means lives at stake. But EHang has already solved this. In March of 2025, the first air operator certificates were issued in China for commercial human-carrying autonomous eVTOL operations. That means paying passengers. That means regulated commercial service. That means EHang EH216-S operators have already flown over 1,000 commercial flights in cities like Guangzhou, Hefei, and Shenzhen. The tension deepens when you realize the scale of what's coming. EHang is expanding its Yunfu facility from 24,000 square meters to 48,000 square meters, targeting 1,000 units of annual production capacity by the end of 2025. They're building a second factory in Hefei. A third is planned for Abu Dhabi. While Joby Aviation in America is still waiting for FAA approval, while Archer is conducting power-on testing, EHang is already in commercial operations and ramping production. But autonomy demands something that assembly lines alone cannot provide: artificial intelligence that learns, adapts, and makes split-second decisions in urban airspace. The software running through these aircraft is the product of machine learning trained on millions of flight simulation hours, thousands of real flights, and continuous data collection from every operational aircraft in the fleet. Each new flight makes the system smarter. Each aircraft that rolls off this line is safer than the one before it because the collective intelligence improves with every unit produced. This is the future of transportation, and it's not coming from Silicon Valley or Stuttgart. It's being manufactured right here, in Yunfu, at a rate that's accelerating every quarter. Electric propulsion and battery systems. You stand in front of the propulsion assembly station, where the true heartbeat of these flying cars is being installed. 6 electric motors, 8 motors, sometimes more, depending on the design. Each one is a compact, brushless electric motor capable of producing thrust measured in pounds while weighing just kilograms. These aren't the motors in your electric toothbrush. These are precision-engineered components, where efficiency is measured in fractions of a percent because those fractions translate directly into flight time and payload capacity. But the motors are only half the equation. The real miracle happening in this factory is battery integration. Lithium-ion cells are being assembled into modular battery packs, each one wired with intelligent battery management systems that monitor voltage, temperature, and charge state in real time. You're watching engineers carefully place each cell, test each connection, because a single faulty cell doesn't just reduce range, it could cause a catastrophic failure at 3,000 feet. The tension is invisible but absolute. A fully loaded flying car weighs around 2,600 pounds. The battery pack represents 40% of that weight. Engineers are constantly pushing against the same constraint that has limited electric aviation for decades: energy density. A gasoline engine produces 1,4,700 watt-hours per pound. A lithium battery produces around 260 watt-hours per pound. You heard that right. Gasoline wins by a factor of more than 5. So every engineering decision in this factory is shaped by that brutal reality. Lighter structures, more efficient motors, smarter battery management, distributed propulsion to reduce losses. Walk through the battery testing facility, and you'll see cells being charged and discharged in controlled environments. Thermal imaging cameras track temperature during every cycle because overheating is the silent killer of battery packs. The facility runs 24-hour cycle testing: charge, discharge, measure, repeat, to validate that each batch of batteries can handle thousands of charge cycles without degradation. EHang's current aircraft can fly for approximately 30 minutes on a single charge. That limitation doesn't sound impressive until you realize it covers most urban transportation routes. Most city trips are under 15 kilometers. 30 minutes of flight time is actually enough. But here's where the future gets interesting. Solid-state batteries are coming. EHang has partnerships with battery manufacturers to deploy solid-state technology that could double energy density. That means 60-minute flight times. That means intercity routes become possible. That means the entire economics of urban air mobility transforms. The engineers in this factory aren't just assembling batteries today. They're preparing to integrate technology that will redefine what these aircraft can do. Manufacturing at scale, from lab to line. You're in the quality control section now, watching technicians run diagnostic tests on freshly assembled aircraft. Each one gets plugged into a test rig that simulates flight conditions. Motors spin up to full power. Battery systems deliver maximum current. Flight computers execute autonomous routines. Every sensor fires. Every safety system activates. The aircraft sits suspended in this digital simulation of flight, proving itself before it ever leaves the ground. This is the invisible engineering that separates a prototype from a production aircraft. A prototype might fly perfectly, but can you build 100 of them identically? 1,000? 10,000? That's the question that separates visionary companies from manufacturing powerhouses. And what you're witnessing in these Chinese factories is the answer: yes. The supply chain integration is staggering. Carbon fiber composites come from specialized suppliers who have optimized their production specifically for this application. Electric motors arrive pre-tested from manufacturers who understand that quality variation here is unacceptable. Battery cells come with full traceability. You can literally trace any cell back to the production batch, the manufacturing day, the quality metrics that validated it. This is automotive-scale discipline applied to aerospace manufacturing. But here's the tension that keeps engineers awake at night. One manufacturing mistake could ground an entire fleet. If a single structural defect makes it through quality control and into production, that defect could propagate across dozens of aircraft before anyone notices. That's why the testing is relentless. That's why every component gets verified. That's why these factories employ redundant inspection systems, human technicians catching what automated systems miss, and automated systems catching what human eyes overlook. Walk through the documentation center, and you'll see the traceability systems that track every component from supplier to final assembly. Every rivet has a record. Every solder joint has a test result. Every software update is logged. If an issue emerges in the field, engineers can pull up the complete manufacturing history of that aircraft within seconds. This level of documentation would be standard in aerospace. But applying it to mass production, producing one aircraft every 30 minutes while maintaining this level of accountability is genuinely revolutionary. The factories are also designed for continuous improvement. Engineers work alongside production technicians, constantly identifying bottlenecks, optimizing workflows, reducing waste. What took 3 hours to assemble last quarter takes 2 hours this quarter. What required 10 measurement checkpoints now requires 5, because the process has been refined to the point where quality is built in, not tested in. China's competitive advantage. You step back and look at the bigger picture. Why is China winning this race? The answer isn't rocket science. It's actually simpler and more brutal than that. While Western regulators are still debating safety standards, Chinese regulators have already certified multiple aircraft. While Western companies are treating eVTOL development like aerospace projects cautious, slow, heavily regulated Chinese manufacturers are treating it like automotive development. Iterate quickly. Test extensively. Deploy operationally. Learn from real-world feedback. EHang achieved CAC-type certification in 31 months, using 40,000 test flights. Compare that to the FAA and EASA timelines, stretching 5 to 7 years or longer. You heard that right. China is moving 3 times faster. Why? Because the regulatory framework in China prioritizes innovation and deployment. The government recognizes that urban air mobility represents a trillion-dollar industry, and they're not interested in being a spectator. They want to dominate. But speed alone doesn't explain it. The real advantage is vertical integration. XPeng AeroHT doesn't just design flying cars. It controls battery production, motor manufacturing, carbon fiber composite facilities, and flight software development. When a Western eVTOL company wants to iterate, they negotiate with suppliers. When XPeng wants to iterate, they send an email to another division. That compressed feedback loop is worth months of development time. Government support is real and aggressive. Special economic zones offer tax incentives. Land is provided at favorable terms. Financing is available through state-backed investment vehicles. The Guangzhou Development District didn't just welcome XPeng, it actively invested in the infrastructure around the factory. Flight test zones were designated. Vertiport locations were identified. Investment flowed. This is industrial policy operating at scale, and it's working. But the deepest advantage is cultural. Chinese automotive manufacturers built the world's largest EV industry in a single decade. They learned how to scale battery production, electric motor manufacturing, power electronics, and autonomous driving software. That expertise is being directly applied to flying cars. The same supply chains, the same manufacturing disciplines, the same obsession with cost reduction and quality improvement. Western eVTOL companies are trying to build an entire ecosystem from scratch. Chinese manufacturers are leveraging an ecosystem they already perfected. The tension is unavoidable. By the time Western competitors reach production scale, Chinese manufacturers will have already captured the market. EHang will have delivered thousands of units. XPeng will have refined the land aircraft carrier through multiple generations. The regulatory framework will be established. The vertiport infrastructure will be built. The insurance models will be figured out. The first-mover advantage in China isn't just about being early, it's about being early enough that you define the entire industry. Then came the infrastructure build-out that proved this wasn't experimental fantasy. Urban air mobility infrastructure. You drive to Haixinsha Tech Island in Guangzhou, a facility that looks like something from science fiction. This is where the ecosystem around flying cars is being built in real time. Vertiports landing pads designed specifically for eVTOL aircraft are being constructed across the city, not just one or two, dozens. XPeng has already signed agreements for 60 landing pads at general aviation airports, scenic spots, cultural tourism towns, and urban suburbs. Each one is mapped into the flight planning software. Each one is integrated into the air traffic management system. But infrastructure isn't just concrete and landing pads, it's software. It's the invisible systems that will manage autonomous aircraft, sharing the same airspace. Imagine 100 EH216 aircraft taking off simultaneously from different vertiports in Shenzhen. They can't just fly randomly. They need coordinated flight corridors. They need real-time traffic management. They need weather routing, obstacle avoidance, and emergency protocols that work across the entire fleet. The engineers you meet are building this system right now. Digital air corridors are being mapped through urban airspace. Altitude bands are being assigned. Ground-based radar systems are being integrated with aircraft navigation systems. This is air traffic control for the 21st century. Not humans in towers directing planes, but artificial intelligence managing hundreds of autonomous aircraft simultaneously. The tension emerges when you realize how revolutionary this actually is. Traditional aviation separated airspace from the world below. Airports were distant from cities. Helicopters were rare, dangerous, and expensive. But eVTOL infrastructure is being built into the urban fabric. Vertiports sit on rooftops. Flight corridors pass over neighborhoods. The distinction between air and ground transportation is collapsing. This requires trust. It requires safety margins that don't exist in traditional aviation. It requires a level of autonomous reliability that has never been demanded before. Walk through the Haixinsha Tech Island Visitor Center, and you see the vision being sold to the public. Flying cars aren't presented as luxury toys. They're presented as solutions to traffic congestion. Promotional materials show commuters boarding an EH216 at a downtown vertiport, flying over congested highways, and arriving at their destination in minutes instead of hours. The message is clear. This isn't about innovation for innovation's sake. This is about solving real transportation problems that affect millions of people every day. But the most critical infrastructure isn't physical, it's regulatory. China has designated low-altitude airspace corridors specifically for eVTOL operations. The Civil Aviation Administration of China has established certification pathways and operational guidelines. Insurance companies have started offering coverage for autonomous aircraft. Financing mechanisms have been created to help buyers afford these vehicles. The entire ecosystem is being built in parallel with the vehicles themselves. EHang is operating commercial routes in multiple cities. XPeng is planning commercial deployments. The infrastructure that seemed impossible 5 years ago is materializing in real time, and every piece is designed to support one thing: scaling these vehicles from thousands to millions, from experimental to operational. You visit the vertiport where the first commercial EH216 flights are departing. Real passengers, real money changing hands, real aircraft, making the transition from prototype to operational transportation. This is the line that separates the past from the future, and you're standing directly on it. Current production numbers tell the story. EHang delivered over 200 units of the EH216 series in 2024, a 315% increase from the previous year. By the end of 2025, that number is projected to reach 1,000 units annually. XPeng has received nearly 5,000 pre-orders for the land aircraft carrier, with mass deliveries scheduled for 2026. These aren't prototypes sitting in museums. These are aircraft being manufactured, delivered, and flown by paying customers. The tension is palpable because this represents an inflection point. For decades, flying cars existed only in concept. They were the punchline of future-focused presentations. Someday, people said, we'll have flying cars. But that word someday has evaporated. The timeline is now measured in quarters, not decades. XPeng's factory is producing aircraft at 30-minute intervals. XPeng's vertiports are hosting commercial flights. The regulatory frameworks are established. The supply chains are functional. The technology works. But what makes this truly operational, what separates real production from experimental manufacturing, is the service infrastructure. When an aircraft breaks down, who fixes it? Where are the spare parts? Who trains the technicians? EHang has established pilot training programs, maintenance centers, and operational support networks. This is airline-scale infrastructure being built from scratch in real time. It's the infrastructure that transforms a cool technology into a transportation system. Commercial deployment timelines are accelerating. EHang plans to expand operations to over 10 cities in China by 2026. International deployments are already underway. Demonstration flights have occurred in Brazil, Japan, Thailand, and across Southeast Asia. The UAE and Saudi Arabia have signaled interest in deploying these aircraft for urban air mobility. What started in China is becoming global. The question that dominated the flying car conversation for 50 years was always, when will this be real? And the answer for 50 years was, not yet. But standing in this vertiport, watching an autonomous aircraft taxi toward takeoff with actual passengers aboard, the question has fundamentally changed. It's no longer whether flying cars will exist. The question now is, how fast will they scale? And what transportation systems will they disrupt when they do? Redefining human transportation. You step outside the vertiport and look up at the sky. Aircraft are moving through designated flight corridors. Autonomous systems are managing traffic. People are commuting through the air instead of sitting in traffic below. This isn't a vision of the future. This is the present, happening right now, in China. The factories you visited, XPeng AeroHT's facility producing 1 aircraft every 30 minutes. EHang's Yunfu plant ramping production to thousands of units annually. These aren't experimental labs. They're the birthplace of a new transportation category. In 5 years, there will be tens of thousands of flying cars in operation. In 10 years, there will be hundreds of thousands. The cities that built the infrastructure first, that integrated the technology into their urban planning, that established the regulatory pathways, those cities will have transformed how people move. China recognized this moment. While other nations debated safety standards and questioned whether autonomous aircraft were even possible, China built the factories. The factories are producing vehicles. The vehicles are carrying passengers. The passengers are paying money. The money is flowing back into expanded production. The cycle is self-reinforcing, and it's accelerating. This is what economic transformation looks like in real time. It's not a single eureka moment. It's thousands of engineers, manufacturers, regulators, and operators working in concert to take a technology that seemed impossible and make it routine. It's supply chains optimizing. It's quality control systems catching defects. It's software learning from operational flights. It's vertiports being built. It's insurance being written. It's the entire infrastructure of a new transportation era being constructed simultaneously. The engineers you met, the factory workers, the pilots flying these aircraft, the passengers trusting their lives to autonomous systems, they're all participating in something genuinely historic. They're not building the future. They're building the present moment when the future becomes undeniable. And when historians look back at the moment when transportation fundamentally changed, when cities began moving people through the sky instead of across congested ground, they won't point to a lab in California or a research facility in Europe. They'll point to these factories in China. They'll point to the assembly lines you've seen. They'll point to the moment when flying cars stopped being science fiction and became something that engineers in Guangzhou and Yunfu manufacture before breakfast and deploy by afternoon. The revolution isn't coming. It's already here. You just watched it being built.